10:45, right? Started. Okay, we're going to get started with our next speaker. It's 10:45, so I urge people to come back to your seat, and so we can get started the next talk. This is another this is only the only technical talk for research, so I think this is a interesting talk from Dr. Ho-Kun Kim. He's going to talk about security and safety of internet-connected cyber-physical systems. Dr. Kim is an assistant professor in the School of Computing and Augmented Intelligence at Arizona State University. He received his PhD degree in EECS from UC Berkeley in 2017 with a focus on Internet of Things security. His research focuses on cyber-physical systems, computing systems interacting with human and physical world, especially safety and security aspects. His research interests include software and hardware support for time-sensitive, interconnected, and intelligent cyber-physical system. Dr. Kim won the ACM IEEE Best Paper Award and received an IEEE Microtopics Honorable Mention for his research contributions to the Internet of Things and computer architecture research. Dr. Kim, it's a great honor to have you as part of the UND's CARD Symposium. The floor is yours.
Thank you.
People can come forward, please. Can you come into your seat? We're going to get started, okay?
Thank you, Dr. Prakash, for the kind introduction. And yeah, if you could zoom in to my screen, it will be great. Yeah, now I can see that it's a mixture of the stage camera and my presentation. Would that be possible? Okay. In the meantime, let me get started. Let me give you a little more about my background. So I was, okay, I'll just keep talking. I was originally from Seoul, South Korea, and I also spent quite some time, around 10 years in San Francisco Bay Area. And I studied at UC Berkeley, as Dr. Prakash introduced, and there I mainly studied the safety and security of the Internet of Important Things, which I will get to later. And currently I'm an academic. I'm an assistant professor at Arizona State University, and I still work on security. Sorry? Oh yeah, okay. Yeah, I still work on security and cyber physical systems. And before joining ASU, actually, I spent some time in industry, especially at Google's safe browsing team, where I worked on the infrastructure for detecting malware and phishing, and also protecting internet users from attackers. So, yeah, although these things look very different, actually they are related. I'll show you how they are related, how the phishing and malware attack are related to the attacks on cyber physical systems. So this is my research vision. I ultimately care about safety of cyber physical system. And this is a great example of cyber physical system. This is a Perseverance Mars rover. And did you know that this is the first Mars rover with a helicopter? Yeah, this has a helicopter called Ingenuity helicopter, which flies around the Mars atmosphere, which is cool. And it uses IEMU sensor and nav cam underneath it to navigate around the Mars terrain. And there was a small timing glitch, actually a glitch in the nav cam, the camera, which dropped the one frame in the camera, and which led to an incorrect timestamps for the follow-up images. And that actually almost crashed the helicopter to the Mars ground, right? However, NASA engineers did a great job having fallback mechanisms to recover from such disaster. And fortunately, this Ingenuity helicopter was brought back to the Mars rover safely. So this happened 2021. And my vision here for the CPS security is to make sure that cyber physical systems such as this Mars rover or critical infrastructure or operational technology work correctly even when they're under attack. So yeah, cyber physical systems are computing systems interacting with the physical world and the humans, and that includes vehicles, airplanes, warships, or manufacturing systems. And they have been increasingly connected to the network, because with network you can cover a larger physical area. It's much more feasible than wiring all the systems into a single computer. And they have been also increasingly connected to the internet and the cloud. And that's where this term comes, Internet of Important Things. Because unlike the IoT, if you imagine the IoT, you imagine small things, right, sensors. But actually this includes Internet of Important Things, including the critical infrastructure such as transportation, power grids, environmental monitoring, or remote healthcare. So internet connectivity for cyber-physical systems and Internet of Important Things benefits from the connectivity, because they can leverage the intelligence and data collected over the internet. They can collaborate with each other over the computer networks, and they can cover wider physical area because of the connectivity and distributed nature. Also, that allows remote control and operation, especially when it's dangerous for human operators. For example, during the COVID-19 area, the internet connectivity to critical infrastructure allowed the operators to keep working on those systems without actually being there in person. Also, in case of nuclear accidents, we can get help from this internet connectivity. However, that also means that we connect the important things to the wilderness called the internet, because the internet is full of bad actors, bad guys, and also continuous attempts to break in. So yeah, that was my the introduction of my talk. And let me move on to the first main topic of my talk, risks and threats and how these attacks work. So this is an infographic from the Office of the Director of the National Intelligence. And this shows the attacks that we observed over the 6-month period starting from November last year until April this year. And as you can see, a lot of critical infrastructure in the United States, including agriculture, education, energy, healthcare, manufacturing, government, telecommunication, and even water systems. Luckily, you don't see North Dakota here. North Dakota was not one of the victims, but you can see that lots of states were affected, even only within a half year period. And this is one example, a state-sponsored hackers group called Cyber Avengers. This is not a typer. This is Avengers with a 3 inside, and they hacked the water system of Aliquippa, Pennsylvania last year, and they targeted remote water stations, and they showed these scary screens instead of the operational screens of the computers. Another example here is an attack on the water system of 3 towns in Texas. This just happened about 6 months ago. And the hacker group actually caused the water tank to overflow, so actually damaging the infrastructure. And there have been lots of attacks on other types of critical infrastructure, such as Texas power grid, Hawaii water utility, and so on. So how do these attacks work? I think in the morning sessions, the speakers covered some of them. And actually, we also, the first keynote speaker, Mr. Rees, talked about Stuxnet. And this is a more advanced version of, you can think of this as a more advanced version of Stuxnet. It's called Triton malware attack. And it was state-sponsored and targeted Saudi Arabian petrochemical plant, actually intended to release toxic gas and cause explosion. Actually, the operators there managed to shut down the system infected before anything bad happened. So nothing bad happened, but this could have been a disaster, actually hurting people. And as you can see here, this is where the phishing and malware comes into play for the attacks on cyber physical systems, because they are now connected to the internet. Because the employees use their accounts to log into the system and use VPNs to connect to the industrial control system. And because of that, if you have a malware installed on your computer, or you have an account takeover due to a phishing attack, the bad guys will be able to access the employee's account to mess up with the industrial control systems and cause the damage, physical damage. Another example, I think this was brought up in the morning sessions, and Colonial Pipeline attack, it was a ransomware attack, and the attackers made the critical data, critical operational data unavailable, and people in the eastern US suffered for fuel shortages for 6 days. Again, if you look at the analysis of this attack, you will see that the attackers used the leaked passwords found in the dark web, probably the victims of the phishing attacks, and used it to bypass the VPN gateway of the system, industrial control system, and launched this ransomware attack. So other than that, we also have vulnerabilities in physical side. For example, the attackers can launch a sabotage on the systems that are publicly accessible, or even use an explosive to cause a physical attack, or physically making the systems unavailable. So I went over the risks, threats, and how attacks work on this Internet of Important Things. Let me move on to the future vision of these attacks and research questions and challenges. So usually these attacks follow this pattern of first compromising the inside computer or accounts, then start reconnoitering and spreading the malware, and when it's the right time, they launch an attack. So, yeah. So first step, compromising inside accounts or computers, using zero-day exploits or system vulnerabilities, which will be far more difficult compared to phishing, social engineering, and leaked passwords, because people are much easier to attack on rather than the servers or firewalls directly. And also, they may leverage the physical proximity to use side channel attacks, which I will get to later. So in the future, you will, it's safe to assume that some intrusion will always happen, right? It's impossible to completely shut down such intrusion. And in the second stage, the malware will try to infect other computers until reaching the target computer, actually directly controlling the industrial systems. And in this reconnaissance stage, the malware monitors and silently hide and wait for a chance to infect other malware. And they are very smart. So although there are lots of work on IDS, intrusion detection systems, they are not perfect. So even with the signature-based or anomaly-based, so you can assume, again, intrusion detection beforehand may not always be possible. And the third stage, the malware wait for the right time until launch the attack to maximize the damage to the system. And they either send destructive control signals and make the system unavailable, or damage the critical operational code or data. And at this point, it becomes a matter of mitigating and limiting the damage instead of preventing. So there are lots of points to think about. Just a simple shutdown or reboot is not always a solution in this case. And timing of detecting attacks is critical. And immediate decision making or even quarantine will be important. And we definitely need fallback mechanisms, because we know that this will happen in the future. Also, resiliency and redundancy will help. For example, if you have multiple copies of the operational data, then you should be able to resist the ransomware attacks. And there should always be a way for timely manual intervention where human operators can manually shut down the systems or quarantine the system if necessary. So research questions to defend the future attacks on these internet connected cyber physical systems or Internet of Important Things. So of course, we cannot give up the benefits from the internet connectivity. So we will have to think about how we can ensure critical infrastructure works correctly, or at least does not harm people, even when they're under cyber attacks or physical attacks. Also, we need to be prepared for evolving more challenging attacks in the future because, of course, the attackers, the bad guys will be leveraging the new technologies, generative AIs, or deepfake. And the last one is how to deal with the various challenges in secret systems. And let me go into the various challenges that I noticed and everyone noticed in this field. So first one is heterogeneity. So if you look at these internet-connected cyber-physical systems, or IoIT, you will see that there are lots of components. They have sensor networks and also critical controllers working with the nuclear power plant, right? So each component of the system will have different security requirements. Maybe you need a maximum security requirements and a bunch of fallback mechanisms for nuclear power plant, but do we need that for forest fire monitoring system? That might be an overkill. So we need to think about the heterogeneity in security requirements and resource availability. Also, the connectivity will be heterogeneous among these systems because some of them will be connected directly to the LAN, or some of them are using wireless communication, or even energy harvesting mechanism, and they are only powered only a certain portion of the day. And also, there are lots of domain-specific knowledge required to manage this system or defend this system more effectively. And another thing, I mentioned this earlier, but they have physical proximity and even wireless access. So let me show you a few examples. So this is the research work by the researchers at KTH Sweden. And this is one of the side channel attacks where the attackers leverage non-regular channels like power, thermal, radio signal, or even sound to guess what the computer is currently doing, or even what cryptographic key it is using. So in this case, they used the far-field electromagnetic signal emissions from the Bluetooth communication to guess the AES-128 cryptographic key. So for those who are not security experts, this is an encryption standard used everywhere, basically everywhere. And these researchers were able to use deep learning, and over this, by training over the traces, they could actually recover the encryption key, right? The standard encryption key used in standard mechanism, cryptography mechanism. And another attack demonstration by the researchers at University of Michigan, Ann Arbor. They tried to hack. So I think everyone has seen this traffic controller on the streets, right? They're open, anyone can approach to it, right? And they were able to, so there was a very simple replay attack to take over the control of the traffic controller. And they made all the traffic lights green, which sounds very dangerous. Right? So because of this challenges of being physically proximate, not like the computers secured in data centers, these cyber-physical systems at a much higher risk of being compromised, and we need to have a mechanism to revoke access in case of they're compromised. And another challenge is the scalability. Scalability in terms of both the number of devices and also the data traffic generated by these devices. So We will see the similar trend in Internet of Important Things as in the normal IoT. This is one example. The Waymo self-driving cars back in 2016, each car generated over 4 terabytes of data per day. And now in 2024, it should be much more than that, probably tens of terabytes per day per single car. So we need to come up with an idea how to protect this massive data and massive number of devices efficiently, cost effectively. And another challenge is the low latency and real-time requirements. Let's say you have a very powerful solution to protect these devices, and it takes 1 hour to figure out whether this is an actual attack or not, right? Sometimes it'll be too late, simply just too late. If it takes too much time to figure out whether this is an attack or to launch defensive mechanisms. So the security protocols and operations must be agile and prompt, and if a failure to respond in time can lead to a catastrophic results. One example is autonomous emergency steering or braking in internet-connected autonomous vehicles. So in summary, we need to consider safety, security, and real-time responses. These are critical. Also heterogeneity, hostile environments, open environments, scalability, battery-powered devices, usability, and heterogeneous connectivity, and high dynamicity, especially for those devices that are mobile. And of course, the government noticed this, and there are research opportunities. This is an executive order from 2021 on improving the nation's cybersecurity on different domains of critical infrastructure in the United States. So yeah, that was future attacks and research questions and challenges. And now let me move on to the most technical part of my talk, my research work. And if time allows, I'll also go into the details. So as you have seen so far, the protecting cyber-physical systems from failures or attacks is fundamentally different from securing the general computers or data center cloud servers, because we need to consider the system level design. For example, how they're connected and how they operate, which parts are critical and which part needs redundancy. So it's more about dealing with the complexity or efficiency rather than studying mathematics, number theory, cryptography. So they're very different. So, and I'll also move on to the important concepts for understanding my work. I think many of you are familiar with authentication and authorization, but let me just review. So authorization is an access control. For example, can I enter this building at University of North Dakota after hours? So that's an access control problem, right? You don't want to let anybody enter after hours, right? So same goes for computers and cyber-physical systems. Allowing or denying access to important resources is authorization or access control. Sometimes revocation of access becomes important. Imagine you're an important person managing this building. If you lose your ID card, you want to have it immediately revoked, right, from the access to this building. And authentication, I call it a prerequisite for authorization, because without knowing who you are or what this device is, we cannot tell whether we should allow access or not, right? So this authentication problem includes whether telling whether you're a member of staff at UND or whether you're admin of a company. So this is essential for authorization. So moving on to my work, this is a project, open source project that I've been working on almost 8 or 9 years since when I was a PhD student. This is an open source project called the Secure SORM Toolkit, and I will call it SST. And this is a software toolkit for providing critical authentication and authorization services for internet-connected cyber-physical systems and Internet of Important Things. And this is available on the GitHub. You can simply find it on github.com/IoTauth. And this also received the ACM IEEE Best Paper Award in CPS Week 2017. So let me talk about what this means. Locally centralized, globally distributed, and how this benefits the security services for the IoT. So this is an illustration of this architecture of SST. And you will see lots of these yellow circles over there. And they're called auth. This is a key component in SST, authentication and authorization entity software to be deployed on edge computing devices. And they are locally centralized, meaning that they can be installed on local edge computing servers right next to the important things. So you can have it configured, tailored to your security requirements. And of course, it'll have low latency for security services. And this will also allow immediate quarantine and access revocation if necessary. And it'll work even without the internet connectivity in case of emergency. And they are also globally distributed, meaning that decentralized, there's no single point of failure. And because of that, it's more scalable and highly reliable, and it's easy to bring the robustness and redundancy due to the globally distributed nature. So scalable with an increasing number of devices and traffic. If we assume that the amount of communication for each device stays the same, we can theoretically mathematically prove that it's scalable independent of total number of internet connected devices, as long as we can add more auth accordingly, proportionally. And this provides security support for heterogeneous cyber-physical system environments in terms of key distribution, underlying communication protocols, and cryptography, and so on. So it can provide many different configurations to support different elements, for example, battery-powered sensors and industrial control systems. So it provides trade-offs between security and resource overhead. And it was also formally proven using the formal verification tool. Formally proven to be secure. And I've been also working on the programming platform to make it available for a diversity of the users. For example, people who are not familiar with security at all, or people with different needs. This is still an ongoing work, and this is an API, the diagram showing API encapsulating and abstracting the security-related operation away from the users so that they don't have to worry about. And we also released the API in C programming language last year, so it still keeps evolving and updated. There are lots of work to be done left. And it can also support heterogeneous communication modes. For example, it can support the programming API pops up or point-to-point connections. And we also evaluated the low latency and low overhead of this programming platform. And this is even more technical details. This is the work, the most recent and sizable work to defend against DDoS attacks on this system. DDoS stands for distributed denial of service, and availability of the IoT is critical. For example, if the power grid becomes unavailable, that means a blackout. So this SST's architectural mechanism enhances the availability. Let me briefly show you. So for example, if you're using the Amazon's AWS IoT for the authentication and authorization services, if the cloud is down or even your internet connectivity is down, your system will be down as well, right? But with the edge-based decentralized solutions, even if some of these auth entities are down or the internet connection is down, you should be able to do still provide authorization services to your local devices. And to make it even more secure under DDoS attacks, we developed a mechanism called secure migration, and the goal is to resist this kind of unavailability of some auth. And this is based on replication and distribution. So similar ideas have been used in general distributed systems, such as content distributed network. And still, we have still the same challenges. So how can we provide this secure migration even when some of these auth are down? So let's assume that these IoIT devices are authorized by this A1. And during the normal operation, we decide which information should be distributed to nearby auth. Then we keep monitoring whether this auth is alive. A simple heartbeat protocol will work. And if this is discovered that this is down, then we trigger this secure migration immediately so that these devices can still get access control services by other auth. So actually, there can be multiple possible migration plans, and we need to choose which one works the best. So one thing to consider is the trust relationships between auth or between the devices. For example, in this case, T1 used to be authorized by A1. And to continue this access between T1 and T2, we need to migrate this device to A3 here rather than A2 here. So trust relationship and also critical communication path are important to consider. Another thing to consider is the wireless signal reachability. So for example, you don't want to assign a new auth that is too far away from the wireless devices. And so migration plan can be constructed as an ILP problem in initial linear programming. Actually, I'm not good at math either, but there are tools that you can leverage to run this optimizer. You don't have to understand, you only need to understand how to formulate this problem, and this solver will do. I don't even know how this solver works, but I know it works. So yeah. So it's in this research work, we optimize the availability, maximizing the number of critical components still working and being authorized, even under DDoS attacks. How are we doing about time? It was 12 minutes? 5 minutes, okay. Actually, yeah, this is just experiments showing that this works well. And I also extended my work to cover the security of the data, massive data generated by the IoIT and internet-connected cyber physical systems. And we leveraged, actually this is work in collaboration with my students, and we used a file system called IPFS, highly distributed file system like muTorrent. And we secured the access to this file system using SST. And we're also working on making even larger scale distributed key value storage secure. And here are more my domain-specific research on internet-connected cyber-physical systems and IoIT. One is the precision agriculture. So I've been working on this with my students, sponsored by NSF, IUCRC. And you just saw the cool rover running between citrus orchards in Arizona. And this is an indoor farm called hydroponic, using growing the plants based on the water or liquid solutions. And so connected autonomous vehicles are one of my research areas. And I've been also working with researchers at HP Labs and digital twins for advanced manufacturing. As you can see, all these cyber-physical systems require internet connectivity. So of course, it's important to secure all these systems. And you'll notice that we really need multi-disciplinary research to make them secure. So in conclusion, so safety critical cyber physical systems connected to the internet or Internet of Important Things are under consistent risks and threat of the bad actors. And attacks are evolving and will be more challenging to defend against, so we should be prepared. And we need a resilient, reliable, scalable, low latency security solutions for these. And the security solutions also must support domain-specific heterogeneous requirements and should work under highly dynamic and resource-constrained environments. So that wraps up. I'm open to collaboration. Thank you so much for your attention. I'll be happy to take questions.
Now we're open for questions. So raise your hand if you have questions, please, for Dr. Kim.
Are you open to working with unmanned aircraft systems with the Internet of Important Things?
Of course, like UAVs, drones, right? Yes, actually, I plan to build a UAV for precision agriculture, and we can also use the same drone for pen testing or trying attacking the communication, whether it can resist the replay attacks for control signals. Yes, I'm open to that. Yeah, thanks for the question.
Can you talk about the IUCRC Precision project? I think I'm more curious about it because we also have a new NSF IUCRC funding for critical infrastructure. So, what are the companies involved and in terms of, that research projects that you have?
Oh, yeah, sure. I can briefly talk about the center itself, although I don't run the center. It's run by my senior colleague, Dr. Sarma Vrudula, and the center is called IDEAS Center. Actually, I think that stands for Intelligent Distributed Embedded Applications and Systems, if I remember correctly, and it involves lots of companies on hardware, embedded systems, and cyber physical systems. And I work with a company based in Canada to do data collection on local citrus farms in Arizona. Actually, Arizona, you may think it's only desert, but actually, as long as we have water supply, because we have sunny days, almost 330 days of sunny days. So it's a perfect environment as long as we have water to grow plants. So yeah, it's a very interesting project. And I proposed a collaboration with the company so that the company can benefit from our research activity, collecting the data, and we can also work on the design of the precision agriculture systems. Hope that answers your question.
Thank you. There's one more question.
So you specifically, how much do you know about vulnerability testing within your site? Do you mainly handle that, or is that mainly other people's job? And what do you know about it?
Okay, very good question. Actually, I didn't have much opportunity to run pen testing on our system. So far, I've been solely relying on the formal verification rather than having someone like red team activities yet. But after I joined ASU, we have a very strong cybersecurity team. So I plan on working with those teams because I cannot do everything, right? I'm a guy building the systems and making the secure rather than doing the pen testing. But I'll be happy to collaborate with the colleagues in my institution or with anyone around the world for pen testing these systems. But yeah, so far I haven't been doing serious pen testing yet. Yeah.
So, Professor, you just talked about the scalability within your project, and you've been talking about Internet of Important Things. So, my question is, like, Did you see one of the aspect on node or device and security and ongoing authentication process? And if that is part of your project or you've been exploring, how you manage that communication overhead between your IoT device and edge devices?
Edge devices. Okay, very great question. So what I've been doing, I hope this answers your question. What I've been doing is providing configurable parameters for the domain-specific users. So for example, depending on the power consumption or power budget of your device, you can configure so that, for example, although I didn't talk about that in detail, you can set up the validity period of the cryptographic key differently for different devices. And you can choose to run UDP instead of TCP for the devices that cannot afford the entire TCP stack, or it also provides capability to encrypt the communication, broadcasting communications, for example. That way you can adjust the security guarantees and also power consumption. Hope that answers your question.
Any other questions? If not, let's thank the speaker, Dr. Kim. Thank you, Dr. Kim. And we have almost lunchtime, but I want to just take 2 minutes for recognize our sponsors again. Microsoft, Waterfall Security, Towson, Dakota State University, High Point Networks, Network Center, IEEE Communication Society, NDUS System, CISA, and Alzheimer's Association. Thank you again for your sponsorship for this event. What we're going to do, we have 3 more minutes, but I want to invite Dakota State University Dean Mary for just spend 2 minutes because they're a great sponsor for this event. So at some point, maybe in future years, we can do some co-hosting, or we'll see what we can do. If you want to say a few words to the conference.
Thank you very much. I really appreciate a minute just to be up on stage. Really quickly, Dakota State University, we're South Dakota, and it's close to Sioux Falls. It's a small university, but we do hold all 3 of the CAE designations, the Center for Academic Excellence in Research, Cyber Defense, and Cyber Operations. We focus on a concept that we're in the process of trademarking, and it's called Power Cyber. So if you think about a triangle, you have artificial intelligence on one of the points, you have cybersecurity on another, and then you have quantum computing on the 3rd point. So that's Power Cyber, and we kind of work our degree programs around that. We do have a table back here. We mostly are here talking about our graduate programs, but we do have cyber operations, we have cyber defense, we have certificates in quantum that we offer. We have one of our leading quantum researchers is with me here, Dr. Wadyan. So if you want to talk more about quantum, he's raised his hand there for a second. And quickly, so through that, we have the Center for Quantum Information Science and Technology that we've started. So really working into these areas. We are hiring. We have tenure track positions that we're hiring, and we have instructors that we're hiring. And the last thing I'll say, and I appreciate Jamie mentioning it, we have a conference that we run every year. It's called DakotaCon. It's in March. It's actually free. So if you have the interest in going, it is a professional conference. So the first day, it's all professional speakers. Again, it's a free conference to attend. We do have a capture a flag event with it. And then we have trainings that if you want specific, very detailed trainings, kind of like you would go if you went to DEF CON, you would get those trainings, paid trainings for those. So thank you very much. I really appreciate it. Thanks so much for having us.
Thank you so much.